Welcome to Homework Lib.
Hi, so in this problem we're going to calculate the change of energy for the photon for two different systems. One is the hydrogen atom. Uh, Another one is going to be the lithium 2 plus atom, the one that is asked for us. So the formula for the change of energy of the photon is this one. We have the constant. In this case, it is it's called in general the Rydberg constant, but depending if you're doing a spectroscopy or energy, the value changes a little bit. And the formula tells us that the change depends as 1 over n squared. In this case, we're dealing with the transition from n final equals 2 from n initial equals 1 to n final equals 2. So these values, n final and n initial, are going to transform into the final state is 2 squared, so 4 minus 1. Okay? 1/4 minus 1, this is going to be minus 3/4. So the change of energy of the photon, it is going to be minus 2.18 times 10 to the minus 18 joules times z squared multiplied by minus 3/4. But the minus with the minus on this other side is going to cancel. And the 3/4 just end up like this. So now we can proceed with the calculation. For the case of hydrogen, we know that Z equals 1. So this becomes 2.18 times 10 to the minus 18 times 3/4 directly. And for the case of lithium 2 plus, this becomes, and of course this is going to end up being in joules. For lithium, Z is equal to 3, so Z squared is 9. 9 times 3, it is going to be 27 divided by 4. And again in joules. So the result is equal to 1.635 times 10 to the minus 18 joules and 1.4715 times 10 to the minus 17 joules. So you may realize that the change of energy of the photon in lithium is 1 order of magnitude larger. That is because this change of energy of the photon of lithium is 9 times the change of energy of the photon in hydrogen. So the next step is which atom would absorb the longer wavelength of light for this transition. And in order to do that, let's remember the relationship between energy and wavelength. We know that energy is equal to h times frequency, which in turns we can transform it into h times c divided by lambda. Therefore, lambda, it is going to be hc divided by the energy. In this case, we're dealing with changes of energy for the photon. Okay, so with this, we can now calculate lambda for hydrogen, which it is going to be our value for the H constant, that is 6.626 times 10 to the minus 34 joules second. The value for C, that is 2.998 times 10 to the 8 meters per second. And this is going to be divided, in the case for hydrogen, by 1.635 times 10 to the minus 18 joules. And our result for lambda will be 1.215 times 10 to the minus 7 meters. And this lambda corresponds to 121.5 nanometers. So now if we repeat the calculation for lithium, the only thing that is going to change, it is going to be the value for energy, this part over here. So replacing that value with the one that we found, with this one, we get the result of, we get, oh, change of color, we get 1.35 times 10 to the minus 8 meters, which if we transform this into nanometers, it is going to be 13.5 nanometers. So the largest wavelength corresponds to hydrogen, and that makes sense because if we look at this equation and the transform version, if the change of energy is higher, that means that the wavelength it is going to be smaller. So we found that the change of energy for lithium was larger than for hydrogen, so it makes sense for the value to be smaller. And actually, if we just divide the result for hydrogen by 9, that was the factor of energy that we found, you are going to get the value for lambda. And that will be all.